In previous videos, we've talked about equilibria and solutions with weak acids. In this video, we're going to talk about equilibria and solutions with weak bases. So if we have a weak base in solution, then we get the conjugate acid of that weak base, and we get the hydroxide ion as our products. So just as we can write an equilibrium constant in a solution of weak acid, we can write an equilibrium constant in a solution with a weak base. So our base dissociation constant, which is the equilibrium constant when we have a weak base, is the concentration of our conjugate acid times the hydroxide ion over the concentration of our base. For example, if we take something like ammonia, which is a weak base, that forms the ammonium ion, which is the conjugate acid of ammonia, and the hydroxide ion. So we can write a Kb expression, which is the concentration of our ammonium ion times the concentration of the hydroxide ion over the concentration of ammonia. So let's look at an example where we need to calculate the pH of a solution that contains a weak base. So we've actually already written a Kb expression. The question asks us to calculate the pH of a 0.40 molar NH3 solution. So at 25 degrees Celsius, Kb is 1.8 times 10 to the negative fifth. So we'll go ahead and rewrite the expression for Kb. So the concentration of our ammonium ion times the concentration of our hydroxide ion over the concentration of ammonia. So we can't calculate the concentration of H2O plus directly, which is what we need to calculate pH. But we can calculate the concentration of the hydroxide ion. And if we calculate the concentration of the hydroxide ion, we can then calculate H3O plus using the Kw expression. So we're going to set up an ice table and calculate the concentration of the hydroxide ion. So we have our initial concentration, our change in concentration, and our concentration at equilibrium. So for NH3, we had a concentration of 0.40 to start with. And in the very beginning, we're not going to have any of the ammonium ion and the hydroxide ion. As this reaction proceeds, we're going to lose some concentration of ammonia, and we're going to form some ammonium ion and some hydroxide ion. So we're going to take 0.40 minus X is going to be our concentration of ammonia at equilibrium, and our concentration of the ammonium ion and hydroxide ion is going to be X. So we can go ahead and substitute into our Kb expression. So we have 1.8 times 10 to the negative fifth, the concentration of our ammonium ion and the concentration of our hydroxide ion is X, and our ammonia is 0.40 minus X. Now to make our lives easier, we're going to assume that the concentration that decreases here is so small that we can assume this is 0. So again, this only works in certain circumstances, but for the sake of our calculation here, we're going to assume that this is negligible. So that gives us 1.8 times 10 to the negative fifth is equal to x times x is x squared over 0.40. And then if we take 1.8 times 10 to the negative fifth times 0.40, let me make that look like a 4 instead of a 9. So 1.8 times 10 to the negative fifth times 0.40, that gives us 2.6 times 10 to the negative 3 equals x squared. Then if we take the square root so that we get x by itself, that gives us, oops, let's back up a step here. So this does not come out to 2.6 times 10 to the negative 3. It actually comes out to 7.2 times 10 to the negative 6. So if you take 1.8 times 10 to the negative fifth times 0.40, you get 7.2 times 10 to the negative 6. And then if you take the square root of that, we get 2.6 times 10 to the negative third. Now, we said that the concentration of hydroxide we represented as X, so this is also the concentration of OH negative. Since that's all we care about, we don't really need to go back and calculate the concentration of the ammonium ion or of ammonia. Now, the question asks us for the pH. So we have hydroxide. What we need to do is calculate H3O+. So the way to calculate H3O+ is to take Kw divided by the hydroxide ion concentration. So Kw is 1 times 10 to the negative 14 over 2.6 times 10 to the negative 3. And if you divide that out, that comes out to 3.8 times 10 to the negative 12. So now that we have the H3O+ concentration, we can calculate the pH. pH is the negative log of H3O+. So we can take the negative log of 3.8 times 10 to the negative 12, and that comes out to 11.41. So the pH of our 0.40 molar ammonia solution is 11.41. So earlier we talked about Ka. Well, if we can go between the concentration of H3O+ and the concentration of OH negative using Kw, then we should also be able to go between Ka and Kb. So if we have the conjugate acid of ammonia, we can write an expression for Ka, and if we have ammonia, we can write an expression for Kb. Well, if you add these two equations together, the NH4 positive cancels with NH4 positive, and NH3 cancels with NH3. So we have two water molecules forms H3O+ and OH negative. Well, H3O+ times OH negative is the definition of Kw. So, to make a long story short, we can multiply Ka times Kb to get Kw. So the mathematics of how we do that is shown here. But the main thing that I want you to take away from this is that Ka times Kb equals Kw. So if you have Kb and need Ka, then you can calculate that by rearranging this equation. So if you multiply Ka times Kb for the ammonium equation and the ammonia equation, you would get Kw. So as I said, Ka times Kb equals Kw. So we can rearrange that. If we have Kb and want Ka, we take Kw divided by Kb. And if we have Ka and want Kb, then we take Kw divided by Ka. So let's take a look at an example. The other equation I should point out here, pKa plus pKb, which is the negative log of Ka plus the negative log of Kb, equals pKw, which is the negative log of Kw, and that comes out to 14. So we don't use that quite as often, but you should be aware of that equation. So let's take a look at an example. Ka for HCN is 4.9 times 10 to the negative 10th. What is Kb for the cyanide ion? So Kb is Kw divided by Ka. So we can take Kw is 1 times 10 to the negative 14. And Ka is given to us as 4.9 times 10 to the negative 10th. So if we divide that out, that comes out to 2.04 times 10 to the negative 5th. So Kb for the cyanide ion would be 2.04 times 10 to the negative 5th. So, the last thing that we need to talk about in this chapter is acid-base reactions. So we talked about back in the first semester of this course that if you react an acid and a base, you get water and a salt. What we didn't talk about is if you react an acid and a base that are different strengths. So we kind of just assumed that we would be reacting a strong acid and a strong base and get water and salt. But we know now that we also have weak acids and weak bases. So not all acid-base reactions just give us a salt by itself that has a pH of 7 in solution. If we take a strong acid and a strong base, yes, we're going to get a neutral salt and water. So, for example, if you take something like hydrochloric acid and sodium hydroxide, if you take HCl plus sodium hydroxide, you're going to get water and sodium chloride. And we know sodium chloride is soluble, so we're just going to have table salt floating around in water. The pH of that solution is going to be pretty close to 0. But what if you take a strong acid and a weak base? Well, if you take a strong acid and a weak base, the acid is stronger than the base, so your salt is actually going to be something that is slightly acidic in solution. So if you measure the pH of this in water, you would find you have an acidic pH. If you have a weak acid and a strong base, the base is stronger than the acid, so your salt in water is going to have a pH that is basic, so above 7. So the one that's stronger is going to contribute more heavily to the pH. So for example, if you have a salt like ammonium chloride, that comes from the weak base ammonia and the strong acid hydrochloric acid. So the acid is much stronger than the base, so we're actually going to get an acidic solution out of that. So we will actually stop here and we will get some more practice dealing with equilibria of weak bases and Kas and Kbs and acid-base reactions in class. So I will see you in class.